How groundwater moves in southeast Minnesota. The Karst landscape.
The karst landscape is located throughout southeast Minnesota.
A map of the Root River watershed in southeast Minnesota is shown. The watershed is divided into three primary landscapes. From west to east they are Glacial Till, Karst, and Bluffland Karst. The Karst region extends northeast beyond the watershed boundary. An animated cross-section of the karst landscape illustrates agricultural fields, two homesteads, bedrock outcrops, and a stream flowing in a valley below. One of the homesteads has a shallow drinking water well, and the other has a deep well. Below the surface is a thin layer of topsoil. Below that lies alternating layers of limestone, shale, and sandstone. In the limestone there are large cracks and a cave. The top of the water table is highest on the left side of the illustration and dips down as it intersects with the bottom of the stream.
Over thousands of years, carbonate bedrock, also called limestone, is eroded away by slightly acidic water in rain and soil, creating karst features.
The camera zooms in and pans left across the landscape as karst features are identified. Enlarged fractures and caves are located in the limestone bedrock. The sinkhole is a depression at the surface and is shown in the upland area near a homestead. The disappearing stream travels across the upland, ends abruptly before the valley edge, and emerges as a spring at the base of the bedrock outcrop in the valley.
Karst features include enlarged fractures, sinkholes, caves, springs, and disappearing streams.
Rain begins to fall and the camera pans left, zooming in on the surface near the sinkhole. The title, Fast Flow, appears, and a scale bar is added to illustrate the thin soil layer.
A thin layer of topsoil allows water to easily soak into the underlying bedrock. Once in bedrock, water moves quickly to shallow drinking water wells, springs, and streams. Although some rain and melting snow moves from the surface to groundwater through sinkholes, most soaks into the ground across the entire land surface.
Water arrows show the fast water movement through the thin soil into the cracks, zigzagging through the limestone, including those under the sinkhole. Light water droplets travel from the surface and flow over the entire region of bedrock, illustrating that water is soaking in across the entire land surface.
The distinction between groundwater and surface water is not always clear.
The question, groundwater or surface water, appears in the title, and the camera pans out to view water arrows moving through the upland disappearing stream.
Groundwater may emerge as a spring, flow a short distance in a stream, and then disappear. This same water could then re-emerge within hours or days, farther downstream again as surface water.
The camera pans right and out to include the valley. Water arrows show movement through the disappearing stream, and water emerging at the base of the bedrock outcrop as a spring. The spring then flows into a stream.
Layers of shale are less permeable than limestone and hinder the downward movement of water.
The camera pans to the left and focuses on the layers of bedrock below the upland. The shale layer is highlighted and is the third layer below the surface.
Instead, water travels sideways, following the easiest path across the shale.
Water arrows illustrate the movement of water from the surface through the fractures or cracks in the limestone. Once the water reaches the shale layer, it begins to travel horizontally across the top of the shale. As it nears the valley edge, it begins to zigzag downward through a series of cracks in the shale and other layers. Different colored water arrows are now used to indicate younger water from above the shale layer and older water traveling from layers below the shale layer. The younger and older water begins to mix near the valley edge and in the stream.
In areas of the landscape where the shale has been removed by streams or erosion, Younger local groundwater from above the shale mixes with older and deeper regionally sourced groundwater.
The title, "What Decade Are You Drinking?" appears, and the camera zooms out to show the complete illustration.
Younger water is often from aquifers located above shale layers and can be just days to decades old. Older water is typically contained deeper in the glacial till and bedrock layers and can be decades to centuries old. In many cases, drinking water is a mixture of both younger and older water.
In the summary animation at the end, rain begins to fall, and the title, "Groundwater Movement in the Karst Landscape," appears. Water movement arrows flow through all of the features previously mentioned. Upland surface water travels through the disappearing stream, where it reemerges as a spring within the valley. This is all young water. Older groundwater is shown traveling from the bedrock, feeding the stream from below. The stream is shown to have a mixture of young and old groundwater. Young water is also shown traveling from the upland surface through the thin soil into the cracks in the limestone until it reaches the layer of shale. The water then travels along the top of the shale until it reaches the valley edge. The credit screen includes the following information. Video production by Minnesota Department of Agriculture 2020. Advising organizations include the University of Minnesota, Minnesota Geological Survey, Minnesota Department of Natural Resources, Minnesota Department of Health, University of Minnesota, Minnesota Extension, Minnesota Pollution Control Agency, Minnesota Ag Water Resources Center, Olmsted Soil and Water Conservation District. Produced by Kevin Keener. Animation and video production by Luke Porter, Moving Tree Media. Written by Kevin Keener, Bob Tipping, Julia Steenberg, and John Barry. Editing, review, and support by Jen Schaust, Britt Gangnes, Greg Klinger, Anthony Runkle, Jeff Green, Yaba Kiersgaard, Margaret Wagner, Martin Larson, Emily Zanin, Kim and Barbara Crawford, Justin Watkins, Dr. Calvin Alexander, Kent and Jude Dornink, Warren Formo, and Kevin Masarek. Funding sources include Minnesota's Clean Water Fund through the Minnesota Department of Agriculture's Root River Field to Stream Partnership, Minnesota Pollution Control Agency, and a grant from the Minnesota Corn Research and Promotion Council. Special thanks to the Minnesota Geological Survey for their assistance with this project.